Welcome to the class of industrial instrumentation. So, this is lesson 16. In this lesson, we will consider flow meter because we are continuing for last several lessons flow meters. This lesson also will cover basically the flow meter, and the contents of this lessons: hot wire anemometer, one of the most widely used industrial flow meters both for the liquids and gases, that we will discuss in this particular lesson. Also we will solve several problems on the flow meter, various types of flow meters. We will solve problems, we will give the problems, and also we will provide the solutions to these problems. Obviously, at the end of the lesson, the viewer will know the working principle of hot wire anemometer, both constant temperature and a constant current type. These are basic two types of hot wire anemometer you will find. So, we will cover both, how it works, what is the signal conditioning circuitry, and advantage, disadvantage, everything will be covered in this particular lesson, along with the problems and solution to the different flow meters. Now, hot wire anemometer, if I look at the principal operations, it is based on the principle of heat transfer by convection between the resistance wire and the flowing fluid. The wire is kept at a temperature which is much higher than the surrounding temperature, and hence the name hot wire is given. It is capable of measuring average velocity and turbulent flow of the fluid. It can measure both average velocity as well as turbulent flow of the measurement. This is a great advantage of this particular flow meter. Okay. And moreover, time constants of this flow meter is also quite small compared to the other flow meters, and it is direct electrical output flow meter. So, if you compare this flow meter with the DP transmitter, transmitter base flow meter, so it is a great advantage of this particular flow meter. Now, elements used is basically a hot wire filament is usually a fine wire of platinum and tungsten. These are basically two wires used. I should say the tungsten is most widely used as a hot wire probe, right. Typical dimensions are diameter 5 micrometer to 300 micrometers. So, it is a quite thin wire, it is very difficult to even see in a bare eyes, it is a very thin wire, and the length is usually 1 millimeter to 10 millimeters. This is to be installed inside the pipe. Please note the one thing is very important, that it is to be installed inside the pipe. It is not a non-invasive type of flow meter. So, you have to cut the flow meters or the pipe and installs with a forked sort of arrangements, so that it will the length of the flow meter will be opposite at 90 degree to the direction of the flow of the fluid in the pipe. You see, this is our pipe, we can see here this is a pipe, okay, and this is a holder, and this is our hot wire anemometer. Okay, this is the hot wire, you can see here, this is the hot wire anemometer. Liquids are coming in this and liquid will go down, right. So, what is this? Basically, we will see that this is basically the heat balance equations is involved in this particular pin. So, that is basic principles of this flow meter, that will be discussed later. Care needs to be taken so that the loss of heat energy due to conduction or radiation is minimized, because basically we are depending on the convection type of heat transfer. So, the conduction loss and the radiation loss is to be minimized. The element is thus jacketed and placed inside the pipe with the help of a fork type support as shown in the figure. Last figure we have shown. Okay. So, this figure we can see. So, it is the fork type of arrangements, it is placed inside the pipe, right. So, at equilibrium the heat balance equation can be written as I naught square RWO equal to U capital U V naught multiplied by A TWO minus TF. This is equation number 1. That is, heat generated in the wire equal to convective heat loss of heat from its surface, right. What is this? Where the legends are, I is the current flowing through the resistance wire in ampere, RWO is the resistance of the wire in ohm, A is the heat transfer area, that is in meter square, TWO is the temperature of the wire in degree centigrade, okay. TF is the temperature of the fluid in degree centigrade. U V naught is the convective heat transfer coefficient, which is in watt per meter square per degree centigrade. You will find this is for the when there is no flow in the liquids, what is the resistance of the wire we are talking about. So, that will come later on, right. So, in addition to that, some resistance will come whenever there is a change of flow or the flow starts to flow, flow starts to act. Now, this also can be written as, that means these equations I am talking of, this equation, this u v naught can be written as, that means I am saying that it looks like this, u v naught. So, if I take a yellow pen, u v naught equal to a b under the square root v, where a b depends on d, k, rho and eta viscosity. This will be discussed. See here, next is, let us come here, where d is the sensor dimensions, that is in meter, k is the thermal conductivity of the fluid, which is in watt per meter per degree centigrade, rho is the fluid density, that is in kg per meter cube, and eta is the viscosity, fluid viscosity, that is in the Pascal second, right. For the sake of the SI units, we are using Pascal second, even though in the industry you will find still people are using the term centipoise, poise and all those things. Since we are here, we are actually following the SI unit, we must, the SI unit of the viscosity is the Pascal second. Now, dynamic characteristics, now we are talking of when it is in steady state. When it is not in steady state condition, what will be the dynamic characteristics? Steady state, there is a convecting heat loss is equal to the heat generated in the thermally heat generated in the wire. But what will happen when there is a certain change? Liquid is flowing in a pipe in a steady state condition. Now, sudden there is a change in the fluid velocity. So, what will happen? So, there is a rate of change of the heat generation. Okay. So, this is no more in steady state condition. So, during that time what will be our equation here, heat balance equation. So, let us look at that. Taking into account the dynamics of the system, we can write, you see, rate of heat input minus the rate of heat dissipation equal to the rate of rise of heat energy, okay, or rate of rise of temperature. So, rate of heat input which we are giving thermally and rate of heat dissipation due to the convecting heat loss from the wire to the surrounding, that is in the fluid medium, equal to the rate of rise of heat energy in the wire itself, right. So, we can write here I square R W minus U V A T W minus T F M C T W D T. You see all the units are slightly different, previous equations we can see here. You see these are all different there. If you look at these R W, T W, T F, T W, T F will remain same because it is a fluid temperature, it does not depend on the temperature of the wire, but all these units, all the legends you will find R W, U V, T W, all things have been changed there. If I look at the previous expression, so where M is the mass of heating element and C is the specific heat of the element. At equilibrium or steady state, we can have the equation 1 as, for incremental change we can write, for there is a change in the wire temperature, okay. So, change of velocity, what will happen? Let us, for incremental change, I has changed to I naught plus del I. T W, wire temperature, previously it was steady state condition W V 0. In the first equations we have written like this, then plus delta T, change of temperature of the wire. R W is the resistance of the wire. In the first equations, in the steady state equation we are written in terms of R W O. Here we are writing del R W plus del R W. Then U V equal to U V naught delta V naught. You see what was our first equation? Let us look at. If I think this is already chosen. Our very first equations, if I look at it, it was like this: I naught R W equal to U V naught A T W O minus T F. This is the equation 1, is not it? Now, we have changed because we say that it is no more in steady state condition, that means there is heat loss, heat generated minus heat loss equal to the rate of heat energy generated inside. So, it has previously, now we have, so now it has new values, we are, it is time varying value. So, these TW, RWs are all time varying, I are also time varying, all these elements are time varying, these are steady state conditions. If it is time varying, I can write incremental increase I naught plus delta I, TW plus delta T, RW equal to RW equal to RWO plus R. So, all these expressions, you see these expression I naught, TW, RW, V naught are used in the steady state conditions, right. When it is not a steady state condition, it will be something different. That is, in that case, you have to use these time varying parameters, right. Where sigma we write delta U, del of U upon del of V, where V equal to V naught, TW equal to T naught. Simplifying, we are getting this expression, but we have to must derive how we are getting this expression. After simplifications, we will get these expressions, right. So, let us look at how we are getting these expressions. Expressions looks like this. You see, initially, let you take a white page, that will be more clear. You see, we had previously, if I take the change the color of the pen, yes, our equation is looks like this. Equation is I square RW is a time varying quantity, U V A TW minus TF equal to M C dTW by dt. This was our new equations or dynamic equations of the hot wire anemometer. Now, I replace I by I naught plus del I. I replace TW by TW O plus delta T, yes. RW I replaced by RWO plus del RW, and UV I replace U V naught equal to plus sigma into delta V, right. So, if I put all this I here, I will get expressions. Here take a new page, I naught plus delta I whole square RWO plus del RW minus U V naught plus sigma delta V A multiplied by TWO plus delta T minus TF equal to MC derivative of TWO plus delta T by dt, right. So, I can simplify this equation neglecting all the multiplications of the terms like delta I, delta W. So, these are all quite small. So, we can neglect this, that means we are neglecting delta I into delta W is small quantity, we are assuming these are all equal to 0. So, I will get expressions I naught or I will get I naught square 2 I naught delta I RWO plus I naught square delta W minus U V naught TWO minus TF into A minus U V naught A delta T minus sigma A TW minus TF delta V equal to M C delta T, sorry, this will be delta T. See, if I take the eraser, right. So, I will take the pen again. Yes. So, I pen again MC delta T by dt. Now, from these expressions I subtract excuse me, I subtract the equation number 1. What is that equations? Let me write down the equation. If I recall the equation number 1, the equation number 1 was, so from this equation if I give it equation number 2, and our equation number 1 was I naught square RW equal to U V naught A TWO minus TF. Okay, this was the equation 1, right. So, what we are doing, taking a new page. So, I am making 2 minus 1, I will get the expression which looks like this, which looks like 2 I naught del I RWO plus I naught square delta RW minus U V naught A delta T minus sigma A TWO minus TF del V equal to MC delta T by dt, right. Clear? If this is our expressions. So, let me go back to the PowerPoint presentation again. So, this is our expression, right. Yes, right. So, this is a sigma equal to partial derivative of u with respect to v when v equal to v naught and Tw equal to T naught. If we have these expressions, we put delta T equal to delta W by Kt, we have delta RT Ki 1 plus S tau B into delta I minus Kb 1 plus tau B into delta B. So, where tau B is given by MC u V naught into A I naught square into Kt excuse me, where Kv we can write is equal to Kt sigma A Tw minus Tf and u V naught A minus I naught square into Kt, and Ki equal to 2K 2Kt I naught Rw naught u V naught A minus I naught square into Kt. Now, see the block diagram representations of our hot wire anemometers. This delta I am giving, this is change of velocity delta V, and this is my change of resistance of the hot wire, right. This is the first order system, as you can see. So, there can be two types of schematic arrangement of hot wire anemometers, that is I am telling, either it will be a constant current or constant temperature, right. So, constant current type and constant temperature type or constant RW type. A schematic diagram of the constant current type, you see here actually what we are doing, that initially we are taking all the resistance equal R1, R2, R3 and RW, and this RS is quite high, right, and we can measure, we can see the current which is passing through this hot wire. Now, this resistance is so high compared to this resistance, you will find due to the change of flow, the resistance, even the resistance will change, the change of current will be insignificant, right. So, current is kept fixed at a certain value that can be measured by that resistance, that by the ammeter. What is that ammeter? These ammeters, okay. With the ammeter we can see whether the currents are remaining constant or not. The resistance R1, R2, R3 are of the same order as Rw. Typically, it should be quite small compared to the RS, and the value of RS is high, right. Generally used to, this constant current type is generally used to measure the steady flow of low fluctuations in the velocity, not good for very high frequency terminal flow. We need some compensation. If you do the compensation, then it is possible to that when lead lag network using, I can make the circuit in such a way so that I can measure the much higher frequency. Otherwise, normally it is not suitable for the low, high frequency fluctuations, so high frequency turbulent of the flow. Now, this is a schematic diagram of a constant temperature type of a hot wire anemometer. You see here it is a auto balancing system. This RW is put on a one arm of a bridge, which is our hot wire, and all other resistance are put, all are same. Now you see what will happen, that if there is unbalance, that means suppose due to resistance change, then what will happen, you see that if there is unbalance, so you will get a, initially it is balanced, there is no output voltage, no error voltage, okay, but some steady state current will flow through this resistance. Now what will happen, you see that if there is a change, so that change will be, if there is an unbalanced voltage here, and that will amplify this voltage amplifier, then power amplifier, so it will give a current, so it will change the current through this bridge, and it will continue till we achieve the balance, right. So it is auto balancing systems we can see here. Here it keeps the resistance RW constant by incorporating the feedback. Now as the velocity increases, RW decreases, thereby creating an unbalanced voltage, and the current increases, which brings back the resistance to the initial value, right. It increases the bandwidth and thereby suitable for turbulent flow measurement also. So it is also for increasing, since we are using feedback, so it is suitable for measurements of the high frequency swirls and turbulent flow. Now this is a block diagram of a constant temperature type of sensors. We can see we have Kb, Ka, E naught is going out. So this is our typical systems. Thus we get, you see, delta E naught by V, this is output voltage divided by the change of output voltage due to the change of velocity, Kb, Kb, Ka, Ro, TVS plus 1 plus Kb, Ka, Ki, so which is equal to K dash equal to upon tau dash V S plus 1. Previously it is only tau V S plus 1. So what is tau dash V? Let us look at. So K dash equal to Kb, Ka, Ro, 1 upon 1 plus Kb, Ki, and tau dash V is equal to, now previously we had tau V this, and naturally what will happen if I decrease the time constants of the system, or my frequency response will increase, is not it? Lower the time constants, I can measure the high frequency. This is a very fundamental, fundamental equations of any instruments or any systems. If a thermometer time constant is large, I can measure the response very fast for a step input. If it is cyclic, obviously also that advantage is there. Thus we see that the system becomes faster since we are dividing this tau V by this factor. So obviously what will happen, by this factor what will happen is frequency, its tau dash V will decrease, and I can measure the high frequency. Now comparison of the constant current and constant temperature type measurements. Disadvantage of the constant current types. The current has to be kept large, and with a sudden drop in fluid velocity it may lead to the burnout of the wire. So this is a typical problem of the constant current type. That means the current has to be kept large, otherwise what will happen, so usually it is large, and if there is sudden fall in the fluid velocity, so temperature may rise, because it is constant temperature, some constant current must flow through this one, so it will burn out the wire. For dynamic measurements, separate compensation networks are required. That means I need a lead lag networks, as I told you earlier, to make the phase compensation, so that I can go for the higher frequency of measurement. You see the drift of the amplifier will come in picture. If I have a drift here, suppose if I have a drift here, so I have a drift here, so that will come in the amplifier outputs, and we will take the output from these terminals anyway. Instability and drift problems, and for small velocity change, noise has to be taken care of separately, or the measurements are erroneous, right, that also you have to think of. Now let us solve few problems on the flow meter. Let us start with the problem number 16.1. We will solve, I will give the questions, then we will solve the problem. So problem number 16.1, you see here, a measurement of the velocity profile prior to the installation of a permanent flow meter in a pipe is needed, right. So we first want to get an estimate of the flow velocity, right. The mean velocity of a high pressure incompressible fluid through the pipe is measured using the pitot tube. At maximum flow rate, the mean differential pressure was found to be 310 pascals, right. We have to measure number A, calculate the mean velocity of the gas at maximum flow rate, calculate the maximum mass flow rate, calculate the Renault number at the maximum flow rate, and the data given are the diameter of the pipe, which is 0.18 meter, then density of the fluid 6 kg per meter cube, viscosity of the gas 5.0 10 to the minus 5 pascal per pascal second. This is given, right. So, let us go one by one. Let us take a white page here. So, we will take a pen. Assuming solution (16.1), we have assuming energy conservation and no frictional or heat loss the sums of pressure, kinetic and potential energies at the impact of the static holes are equal. This is already discussed in the case of when we discussed actually the pitot tube. Anyway, let me straight away write the equations. P1 by rho plus 0 ZZ1, P2 by rho plus V2 square by 2 plus G Z2, right. So, P2 is a static pressure and this is a stagnation pressure. Obviously, P1 will be greater than P2, right, where Z1, Z2 are the elevations of the holes above the bottom levels, that means static hole and the stagnation hole. So, he assumes initially that Z1, now we assume Z1 equal to Z2, hence we can write that V equal to velocity will be equal to 2 P1 minus P2 by rho, right. Therefore, the mean velocity will be given by the mean velocity will be given by equal to 10.16 meter per second. The maximum mass flow rate is given by dm by dt equal to VA into rho, where VA is the volumetric flow rate. So, it will become m dot equal to V pi d square by 4, where d is the diameter of the pipe, into rho Now D here is 0.18 meter. If I put everything there, because rho is given by 6 kg per meter cube. Okay, density of the fluid. So I will get that mass flow rate equal to 1.55 kg per second. This is one answer, this is another answer, right. Now we have to find the Renault number. Let us take a new page. Now the Renault number is given by Re equal to rho Vd by viscosity. Viscosity is eta, we are writing, where eta is the viscosity. So this will become 6 into 10.16 into 0.18 by already given 5 into 10 to the power 5, 5 into 10 to the power minus 5 Pascal seconds. So this will give you 21.94 into 10 to the power 4. Okay. So obviously you can see this is a turbulent flow, right. So this is in the problem number 1. Let us go to the problem number 2. Problem number 2 is on turbine flow meter. Very straightforward problem. Just plug in the equations, you will get the answer. A turbine flow meter consisting of a rotor with 6 blades is suspended in the fluid stream. The axis of the rotation of the rotor being parallel to the direction of the flow of the fluid, right. The blades are rotating at an angular velocity of omega radians per second, where omega equal to 4.2 in 10 to the power 4 q, right, where q meter cube per second is the volume flow rate of the fluid, and the total flux phi t linked by the coil or the magnetic transducer is given by 4.637 phi t 4.637 plus 92 cos 6 theta. This is in milliwebers, right, where theta is the angle between the blade assembly and the transducers. These are all very standard notations which we have given in our particular lesson. So we exactly use the same notations here, right. And the flow meter can measure the flow rates ranging from 0.22 into 10 to the minus 3 meter cube per second and 3.74 10 to the minus 3 meter cube per second, right. Find the amplitude and the angle, find the amplitude and the frequency of the transducer output signal at minimum and maximum flow rate, right. So this is our question number 2 on the turbine flow meter. Let us look at the solution, right. Let us take a white page. So this is problem number 16.2, right. Here we know that phi t theta equal to alpha plus beta cos n theta, right, where alpha is the mean flux, beta is the amplitude of the flux variation, and n is the number of blades. So E equal to, we know, equal to minus d phi t by dt minus d phi t by d theta into d theta by dt. So it will give you now d theta by dt is equal to minus beta n sin n theta, right, and d theta by dt is equal to omega, which is angular velocity. So, theta equal to omega t, assuming that at theta equal to 0 at t equal to 0, right. Now, we can obviously write, let us take a new page, that t equal to beta n omega sin n omega t, right. So, the amplitude of this signal is beta n omega and the frequency is equal to n omega by 2 pi, linear frequency, not circular frequency, by 2 pi, right. So, omega will be frequency for the minimum flow rate will be, if I plug in all the expressions, will become 9.24 radians per second, right, and amplitude will be given by .92, right. .92 multiplied by number of blades 6 into 9.24, which is will be 51 millivolt, right, and the frequency will be this is in milliweber, so this should be in millivolts. Frequency will be 6.6 into 9.24 by 2 pi. This will be equal to 8.82 hertz. Okay. So, this is the amplitude, this is the frequency, right, and this is for the minimum flow, right, minimum flow rate, okay, minimum flow. Now, let us do for the maximum flow. Let's take a white page. For maximum flow, rate, I will get omega equal to, if I plug in all this value, 57.1 radian per second, and the amplitude will come up as, if I calculate, equal to 867.2 millivolt, and frequency equal to 150 hertz, right. So, this is one answer, this is another answer, right. So, these are the another problem, right. So, this is 800, I do not know whether it is eligible, 867.2 millivolt, right. So, the frequency is 150 hertz. Let us do the other problem. Let us go to the problem number 6.3. Problem 6.3 is on the Doppler flow meter. Doppler shift, as you know, there is two types of Doppler flow meters, time shift measurements and the ultrasonic and the Doppler shift measurements. So, let us first do the Doppler shift ultrasonic flow meter problem on Doppler shift ultrasonic flow meter. A Doppler shift ultrasonic flow meter is shown in figure below, which is with its signal conditioning circuitry. Two piezoelectric crystals, each having a natural frequency of 2.4 megahertz, are used as transmitter and receiver. The transmitting crystal directs an ultrasonic wave into the pipe, which makes an angle of 45 degree with the flow. Calculate the received frequency as well as the cutoff frequency of the low pass filter. Okay, why should I low pass filter? Let us look at. Okay, this is our diagram of the systems. That means, you see that there is RF oscillator Okay. So, we are launching the ultrasonic wave, it is getting reflected from some liquid, some suspended particles. It is, as you know, that is Doppler shift ultrasonic flow meter is not for the clean liquids, there should be some particles inside the liquids for which the ultrasonic wave should be reflected by that particular particle. These ultrasonic waves are launched from this transmitter, it is coming here, it is getting reflected and is coming in these directions. You see, we can write here from our previous expression Fr, frequency of the reflected wave, equal to Fi 1 minus V cos theta by C upon 1 plus V cos theta by C, right. This we can write simplify equal to Fi 1 minus V cos theta by C whole square, where Fi is the frequency of the incident beam and Fr is the frequency of the reflected beam, right, of the ultrasonic wave. So, we can obviously write Fr equal to Fi equal to multiplied by 1 minus 2 V cos theta by C, right. Now, one thing you please note that the V cos theta is much less than C. So, Fr will come up as 2.366 megahertz, right. So, this is our, okay, even though it is small. So, this we can, so it is 2.4 is Fi. So, receive signal is like this one. Now, the input signal we can write like this one. Let us take a blank page. Input signal is equal to V sin 2 pi Fi into T, right, and the reflected signal equal to V sin 2 pi Fr into T. So, output of the adder is equal to V sin 2 pi Fi t plus sin 2 pi Fr t, right. So, this I can simplify as 2V cos of 2 pi Fr minus Fi by 2 into T multiplied by sin 2 pi Fr plus Fi by 2 into T. So, this will give you, okay, 2V cos of 2 pi delta F by 2 into T multiplied by sin 2 pi Fr plus Fi by 2. If I put in the first bracket, this will be in the second bracket into T, right. So, you see these equations of a modulated wave with the carrier frequency of this one, this is a carrier frequency, right, and the modulating frequencies is delta by 2, right. Now, let us suppose we write that, make a blank page again. Let me suppose that we are telling delta F by 2 omega m and Fr plus Fi by 2 is equal to, we are writing excuse me. This actually by 2 pi I think, Fr plus Fi by 2 equal to omega c by 2 pi c by 2 pi. If it is there, so quite obviously I can write here the input to the demodulator is equal to V sin omega c plus omega m t plus sin omega c minus omega m into t. If I demodulate with k sin omega ct, so the output of the modulator will be kV sin omega ct sin omega c plus omega m into t plus sin omega ct into sin omega c minus omega m into t, right. So, this will give you kV by 2 cos of 2 Vc omega m into t minus cos of omega mt plus cos of 2 omega c minus omega m into t minus cos omega mt. So, thus when passed through a low pass filter, see if this signal is passed through a low pass filter, the output I will get kV by 2 cos of omega mt. So, that means we have only signals which is consist only of delta f by 2. Now, the cutoff frequency of this low pass filter must be greater than that of delta f by 2. So, what is delta f? Delta f we have seen Fr minus Fi is actually coming as 33.93 kilohertz. So, delta f by 2 I can write 16.96 kilohertz. So, the cutoff frequency we have chosen, is equal to 20 kilohertz, right, say. So, this is the answer of the third problem. Now, you see fourth problem is very straightforward. The problem 6.4, a transit time ultrasonic flowmeter is used to measure the velocity of a gas flowing in a pipe. In such a case, it was found that the zero flow transit time as 1.2 millisecond. That means, when there is a there is no flow in the liquid. So, transit time, the transit of the signal between the transmitter and receiver is 1.2 millisecond, whereas when there is a flow, the differential transit time was 115 microsecond. The angle between the line connecting the transmitter and the receiver and the direction of flow of the fluid is 30 degree. Find the velocity of the gas, and by what will be the transit time change for percentage of 2% change plus minus 2% change in the velocity of the sound. Velocity of the sound in the gas is 500 meter per second. So, this is our problem. So, this obviously is very familiar with. So, let us take a blank page. So, it looks like this. I have a pipe. So, now I have a transmitter here. I have a transmitter here. So, this angle is making with this is 45 degree. Okay. What is the angle? No, this is 30 degree. right. So, this is our L length. So, we see that, so if we say A transmitted B, so TBA is coming L by C minus V cos theta, TAB equal to L by C plus V cos theta. So, delta T I can write L to V cos theta by C square, right. So, this we can write 2V cos theta by C into L by C. So, L by C is the zero flow transit time, L by C is the zero flow transit time, that means when there is no flow, transit time equal to T naught. So, V equal to, I can write delta T by T naught into C by 2 into 1 by cos theta. So, if I plug in all the value, I will get V equal to 27.66 meter per second, right, because T naught also we know, T naught already given. Now, we see that there is a percentage change of the flow of the fluid, right, percentage change in the there is a percentage change in the velocity of the sound, how my measurement will be affected by that. So, let us look at that. So, initially when it is there is no change, that times I describe with T1. So, delta T1 equal to 2B cos theta into L by C1 square, right. So, L by C, C1 equal to 1.2 millisecond, is not it, right, and L I can write taking that there is no change of the velocity of sound, that means it is 500 meter per second. So, I will get L equal to 1.2 into 10 to the power minus 3 into 500. So, it is coming as 0.6 meter, right. So, C1 will come up as 1.02 C1. Actually, this should be C1, I think. So, because this is a no change, so let me take the eraser. So, this should be C1. So, C1 equal to 1.02 C. So, let me take the pen again. Like C1 equal to 1.02 C. Now, there is a change, right. So, there is a change of the fluid velocity. So, let us take again new page. So, the second case delta T1 equal to 2V cos theta L by C square. So, this will become or C1 square rather, it should be C1 square equal to 2V. So, this will be, if I take I am sorry. So, it will be C1 if I write delta T1 equal to 2V cos theta L by C square. So, this will give you, if I plug in all the value, 110.5 microsecond. So, for C2 equal to 0.98 C. So, we have delta T T2 equal to 1.98 whole square into delta T equal to 119.7 microsecond. So, this will lead to the transit time variation. So, the transit time variation transit time variation is equal to plus minus 3.9%. This is our answer, right. Now, let us look at the problem number 5. Problem number 5 is on the electromagnetic flow meter. In an experiment, an electromagnetic flow meter was used to measure the average flow rate of a liquid flowing in a cylindrical pipe. The flux density of the electric field applied to have a peak value of 1.4 Tesla Weber per meter square. The output from the electrodes was fed to an amplifier with a gain of 10, an input impedance of 2.2 megohm. The internal resistance developed due to the fluid between the electrodes is found to be 200 kilo ohm, right. Now, determine the velocity of the liquid when peak to peak output voltage of the amplifier was found to be 4 volt, and find the percentage change in the reading of the amplifier for a 10% increase in the conductivity of the flowing fluid, given the diameter of the pipe as 0.1 meter. So, it will look like that E is equal to here 2 volt. Now, the output voltage will be given by E minus I R internal equal to I into R amplifier, right. So, E equal to E 1 plus R internal plus R amplifier, where E is the voltage induced to the magnetic field and also the open circuit voltage. This basically is the open circuit voltage. So, this will become, if I plug in all the values, it will become 2 1 plus 200 into 10 to the power 3 upon 2.2 into 10 to the power 6 equal to 2.18 volt. Now, we know that the E equal to VLV into the gain of the amplifier. If I have amplifiers, amplifier gain, or the usual notation flux density, length or diameter of the pipe, and V is the velocity of the fluid. So, this will give you, obviously, if I manipulate, that is V equal to E VL multiplied by gain of the amplifier. So, it will give you 1.55 second, sorry, meter per second. I will write again 1.557 meter per second, right. So, if I have that thing, we take a new page. Conductivity increases by 9%, that means conductivity increases by 10%. So, the resistance change, resistance decreases by 9.1%, right. So, R dash will be 0.91 into 200 equal to 182 kilo ohm. So, the output voltage will be equal to 2 multiplied by 2.18 upon 1 plus 182 into 10 to the power 3 divided by 2.2 into 10 to the power 3, like this one. So, this will give you 4.026, right. So, the change of output voltage, if I take a white page again. So, percentage change of output voltage is equal to 4.026 minus 4 by 4 into 100. So, this will give you 0.67%. Okay, this is the answer. So, with this I come to the end of the lesson 16 of industrial instrumentation.